So Doppler effect. Let's say you have a moving object emitting a sound, because that's really all that's needed for Doppler effect. You get a Doppler effect if either the sound is being created by a moving object, a moving source, or if the listener is moving, that also will do it. To start with, let's take a look at the example of a moving source. I think that's probably going to be easier to visualize. Let's say you have maybe a car or something that is producing sound. And we'll call this the source. So this car is able to move around, and it's got, I don't know, maybe its engine is producing sound, or maybe there's a siren on top that's producing sound. And so that's creating sound waves. And let's say at some instant in time, this car has created sound waves. You know, let me make an axis also so we can keep track of distances. This doesn't work so well. Close enough. So here's the axis we're dealing with. So we can at least have some numerical markings. We'll treat this as our x-axis. And let's say this car starts off at location 6. And at that instant, it creates a couple of waves. I mean, it's creating a wave, but let's say it emits a crest here. That crest, we should probably treat as a sphere spreading out from that source, because this sound wave is essentially a high pressure crest spreading out, and low pressure troughs as well, spreading out as a sphere. But let's say we don't really care about all directions. Let's say we just care about the wave traveling forward and the wave traveling backwards. So if we draw that out, we've got a forward traveling crest and a backward traveling crest. Traveling forward and backward from there at the speed of sound, starting at location 6. Now let's say we wait a little bit of time. What's going to happen to these wave fronts if we wait a little bit of time?
They'll move like away.
Yeah, they're going to move away from that source. And let's say we wait long enough for the wave front to move, let's say 2 meters. So that's now at 8, and that's now at 4. Oh shoot, I forgot 5, didn't I? Let me modify that. There, that should fix things. Okay, so if we start at 5, let's go ahead and start at 6. And 5 should be good. So this wave has moved backwards 2 meters. This wave has moved forwards 2 meters. But the thing is, the car itself is not staying still. Let's say the car is traveling, just to pick an absurd example, let's say the car is traveling half the speed of sound. In the amount of time it takes for the sound wave to go 2 meters, how far would the car go?
1.
Right, it's going to travel half that far, 1 meter. And let's say at that instant in time, let's say that's 1 full period. So the car has emitted a crest. 1 full period later, it's going to emit another crest. So at this location, it's now emitting another crest. And we can treat that as both a forward moving crest and a backward moving crest. And now we wait a little more time. Let's say we wait the same amount of time. So the waves travel 2 meters. These forward going waves travel 2 meters forward. These backward moving waves travel 2 meters backward. And during that same amount of time, the car travels 1 meter forward, traveling as it is at half the speed of sound. And then let's say this is enough time that it emits another crest. So we've got a forward moving portion of the crest and a backward moving portion of the crest. We wait a little bit longer. The forward moving waves move forward 2 meters. Backward moving waves move backward 2 meters, and I'm kind of off the chart here. And let me just move everything else away then. That's moved backwards 2 meters. So something like that. So, and then of course, at that point, we would be emitting another trough, or another crest, I mean, because this is another one period of time passing. So we've got a whole bunch of wavefronts we can now measure. We can actually get some information about these. And what do you notice about the wavefronts in front versus the wavefronts behind? I think I forgot to move that. There we go. What do you notice about those wavefronts in the front versus the wavefronts behind? Yeah, in the front, these are, and you can't really directly see frequency, but you can notice just from the, since this is a distance diagram, what would you say about the distances here?
The wavefronts in front are closer together than the ones behind.
Right, these are closer together because they get bunched up. Since the source is moving in the direction of travel, that means that the next wavefront gets emitted a little bit closer than it should be. Closer together means a short wavelength. And that's how we know it's higher frequency, because wavelength and frequency should be inversely proportional. So even though the source is just emitting one frequency, somebody standing in front is going to hear a higher frequency. Meanwhile, what do you notice about the wavelength behind? The distance between these. Yeah, these crests are further apart. And the distance from crest to crest is the wavelength. So we get a longer wavelength and therefore exactly a lower frequency. So you're going to hear a lower note. So you actually hear different notes, different pitches, depending on whether the source is traveling towards you or away from you. That's what we call the Doppler effect. And this is the characteristic sound of a car or any fast moving object traveling past you. It approaches you, you get a high note, and then it passes you. That change in pitch is because it transitions from traveling towards you to traveling away from you. So you transition from hearing these bunched together waves, short wavelength, higher frequency, to hearing these spread apart waves, longer wavelength, lower frequency. So this is physically what's happening there. You're getting these bunched together waves if it's coming towards you, or these spread out waves if it's traveling away from you. Any questions on that so far? And this effect can be amplified even more if the listener is also moving. Like for instance, let's say you have a listener and you are standing here listening to the waves. You're going to hear a certain note. But let's say instead of staying still, you are in the process of moving towards the car, towards the source. If you're moving towards the source, what's that going to do to the frequency you hear? Right. If the listener is moving towards the source, you also hear a higher frequency. Because if you're just standing still, you're hit by a certain number of wavefronts per second. If you're running inwards towards the source, you get hit by more wavefronts per second. Or if you're moving away from the source, then it takes more time for the wavefronts to catch up with you, and you hear fewer wavefronts per second, lower frequency. So the actual frequency you hear is influenced by both the source's motion and the listener's motion. And there's an equation that ties all those together. Have you seen the equation for the Doppler effect yet? The frequency observed equals what? What's your usual equation for that?
Is it wave speed plus minus the speed of the observer over the wave speed plus or minus the speed of the source times the frequency of the source?
Yeah, let me fill that in. That should do it. So yeah, the observed frequency, that is the actual frequency you hear, is the frequency produced by the source, f source, modified by this ratio, speed of sound, or whatever the wave is, plus or minus speed of the observer, divided by speed of sound plus or minus speed of the source. And of course, that's sound or whatever wave you're talking about. You can get a similar effect if you have, like, let's say you've got a boat traveling along the surface of the water. As the boat bobs up and down, it's producing ripples. Those ripples are going to be bunched closer together in front of the boat and spread out further apart behind the boat. So you get the same sort of effect. You would just use speed of ripples in water instead of speed of sound in air. But the exact same principle still applies. In fact, the same is even true with light. If you're talking about light from a fast-moving object, if you have an object traveling towards you, you're going to see higher frequency light than it's producing. Or if it's traveling away from you, you're going to see lower frequency light. For sound waves, frequency corresponds to what pitch you hear, what note. What about for light waves? What would the frequency or wavelength tell you about the light? What would you actually see? Yeah, that's the color. So objects traveling towards you are going to look slightly redder. Objects traveling away from you, sorry, other way around, traveling towards you, higher frequency, that's going to look bluer than it really is. Traveling away from you, it's going to be a lower frequency, larger wavelength, is going to look redder than it really is. And of course, this is only going to be apparent, it's only going to be noticeable if it's traveling at a very fast speed compared to, say, the speed of light, or some significant fraction of the speed of light. For sound, it's usually, or for light, it's usually called redshift instead of the Doppler effect, but it's the same basic principle. Uses some slightly different equations because of relativity, but same idea. Any questions on that so far? So let's try out an example here. Let's say you're standing still. Observer is standing still, and the source is producing a frequency of 400 hertz, but observer hears a frequency of, let's say, 410 hertz. From that, we should be able to figure out how fast the source is moving, because I think that's going to be the only unknown left. And also which direction the source is moving. First of all, if you're hearing a higher frequency, does that mean the source is traveling towards you or away from you? Yeah, if you're hearing a higher frequency, you know the source is traveling towards you. In fact, even from this diagram, we can see that if the source is traveling towards you, the waves get bunched together. That means shorter wavelength and higher frequency, which is exactly what's being described here. So the source is traveling towards the observer. And we should be able to calculate exactly how fast as well, based on the Doppler shift equation here. So let's try filling in what we can. So taking just a copy of this equation, and then we'll fill in some values. Of these values, what do we know? What values or what variables can we fill in here?
We know that the frequency of the observer is 410 hertz, and then the frequency of the source is 400.
Yeah, so we can fill those in. You hear 410 hertz, but we know the source is producing 400 hertz. And do we know any of the speeds involved?
We could fill in the speed of sound, and then the speed of the observer is 0.
Yeah, we know the observer is staying still, so speed of the observer is 0. And speed of sound, what's our usual value for speed of sound? Yeah, that's usually about generally between 340 and 350 meters per second. The exact value is going to depend on things like the temperature and humidity of the air. So it does vary to some extent, but generally in typical air on Earth, speed of sound is about 340 to 350 meters per second. Let's say 350. And these are all going to be in meters per second, so I'm just going to assume we cancel out the meters per second. And then this speed of sound in the denominator is also going to be 350. And we don't know the speed of the source. So that's the last unknown here. Although to solve this, we're also going to need to fill in the plus or minus. What do you think that plus or minus signifies here? Like, how would we decide that? Yeah, this is all about direction of movement. And there's some rules that are possible to memorize for which direction is plus versus which direction is minus, but I can never remember those anyway. So I usually look at it in terms of, should I expect this to be increasing or decreasing the result? For instance, in this case, we're assuming the source is traveling towards the observer. Would you expect that to increase or decrease the resulting frequency? If the source is moving towards the observer, would that result in a higher or lower pitch? Yeah, it should be a higher pitch. You get an increased frequency, and which is also what we notice just based on the given values here as well, 400 hertz and 410 hertz, which means we want this fraction to be larger than 1. However, for the denominator, if you've got something in the denominator and you want to make the result bigger, should you make the denominator larger or smaller? Yeah, to get a larger final result, you want a smaller denominator. So to get a smaller denominator, should we be adding or subtracting? Yeah, I would use subtraction there. So that's generally how I would do this. Instead of trying to memorize rules about what's plus versus what's minus in terms of direction, look at it conceptually as, should you expect this to be a larger or smaller result? And then based on that, do you want a larger or smaller numerator? And also, do you want a larger or smaller denominator? So you can deal with the numerator and denominator individually and choose plus or minus based on whether you want the result to be larger or smaller. And then plus or minus 0 doesn't matter. That's just going to be 350. And then V source is the only unknown left. So we should be able to solve for that. Any questions on the setup so far? So let's work out the algebra then. How would you isolate V source if it starts out in the denominator? Is there any way you can
Multiply by it?
Yeah, if we just multiply both sides by that entire denominator, then that should cancel out the denominator. We just multiply by 350 minus V source and multiply the other side by 350 minus V source. Then those cancel out. So we get 350 minus V source times 410. Equals 350 times 400 hertz. And then what else could we do to isolate V source here? Yeah, if we divide by 410, specifically 410 hertz, then hertz is canceled out anyway. So we get 350 minus V source equals 350 times 400 over 410, which reduces to 40 over 41. And I guess we may as well combine those as well. That's 3,500. So 14,000. Yeah, that should work. So 14,000 over 41 equals 350 minus V source. And then what?
And subtract and then divide by -1.
Yeah, so that gives us V source equals that minus 350, but then we take the negative, so 350 minus that. And notice that that's basically speed of sound minus this fraction. And what does that fraction work out to? 15,000 divided by 41. That's 341-ish. So 350 minus 341 is about 9 meters per second. So that means in order for this to work, to get a 410 hertz sound that you hear out of a 400 hertz sound that the source is providing, the source must be moving at 9 meters per second. So you can figure out how fast the source is moving just based on comparing the sound you expect to hear from that source if it were staying still versus the sound you actually hear. That's one of the many uses of the Doppler effect. Any other questions on the Doppler effect so far? All right, then let's take a look also at the this whole idea of wave interference and the total phase and how that relates to everything. Let me clear this diagram. What has to be happening in order for interference to show up? When would you expect interference to be going on? All this constructive interference and destructive interference stuff. What has to be happening to make that happen?
Would it be that two waves interfere at the same position at the same time?
Yeah, you got to have two waves or possibly more, but we're just going to be looking at two waves for now at the same position at the same time. Two waves trying to occupy the same space. And that way, for instance, if you've got a crest from one wave and a crest from another wave overlapping, those are going to combine into an even larger crest. Or a trough from one wave and a trough from the other wave overlapping, those combine into an even larger trough. Or alternatively, what would happen if you get a crest from one wave and a trough from the other wave in the same position? The crest and trough, what do those do? Yeah, those are going to cancel out. Or as long as there's the same amplitude, they would cancel out completely. If they're different amplitudes, like let's say one of them is, let's say, 5 above the axis and the other is only 4 below the axis, they don't completely cancel out, but they cancel out as much as is possible. They would only truly cancel out completely if they were the same amplitude. But in general, yeah, interference happens when two or more waves occupy the same space at the same time and combine their effects. And that really is just addition. You're just adding y from one wave plus y from the other wave to get the total y value, the total displacement. However, we usually don't want to have to go through the effort of graphing both waves on the same graph and adding together the y values and figuring out the total y value. Usually all we care about is this going to be constructive or is it going to be destructive or is it going to be somewhere in between? And for that, we can use the idea of the total phase of the wave. And this goes back to the idea of the wave equation itself. If you take a look at the wave equation, let me zoom in on this. The wave equation itself, y equals a times sine of all this stuff, all this stuff inside the wave function, the sine wave itself, this is what we call the total phase. In other words, we usually use capital phi to refer to that. So lowercase phi, the little phi here, the phase constant or phase shift, is just the single constant value added in here. Let me label that as well. So that value, the plus little phi, is just some constant value. Maybe it's like a plus pi over 3 or a minus 2 pi over 5 or something. It's just some value in radian measure that establishes the initial conditions of the wave. If you change the phase shift, you're basically just taking the wave at time 0 and moving it somewhere else. The total phase, though, is the entire thing inside the sine function. And the total phase is very useful because that tells you essentially what point on the wave you're looking at. For example, let's say if the total phase at some position and time, because notice that the total phase is a function of position and time. It has x and t in it. Let's say the total phase is pi over 2. That means you're taking the sine of pi over 2. And what is sine of pi over 2? Yeah, sine of pi over 2 is 1, and that's the highest sine can be. So what type of point are we at? Right, that's a crest. What about if the total phase is pi? Sine of pi is what? Right, that'd be 0. So we'd be at equilibrium. No displacement at all. Or what if it's, let's say total phase is 5 pi over 2. What would 5 pi over 2 signify? Trough would be 3 pi over 2, because sine of 3 pi over 2 is -1. But 5 pi over 2 is further than that. Specifically, 5 pi over 2 is how far from that original pi over 2. What's the difference between pi over 2 and 5 pi over 2? Right, that's exactly 2 pi apart. And 2 pi is what? What does 2 pi radians mean? Yeah, I wouldn't necessarily say one wavelength because we're not talking about distance. We're talking about total phase, which is a combination of distance and time. But I would at least say it's one full cycle worth of radiance. So if you start at a crest and you go one full cycle, which might be just distance or just time or a combination of them, but one full cycle away from a crest should be another crest. The next crest, very next crest after pi over 2. And we could keep going. The next, if we take 3 pi over 2 and add another 2 pi, we'd be at another trough. So for instance, 3 pi over 2 plus another 2 pi would be 7 pi over 2. That would be the next trough. In fact, every 2 pi, this cycle repeats itself. The thing is, though, if we're comparing two waves, we don't really care whether each one individually is at a crest or a trough. What we care about is, are they the same? If you've got two waves that are both at a crest, that's constructive interference. If they're both at a trough, that's still constructive interference. If they're both equilibrium on the way up, that's constructive, or if they're both equilibrium on the way down, that's constructive. So the important thing isn't just the value of total phase. The important thing is the difference in total phase between the two waves. And that's this next equation I've got here. This here is the total phase difference. In other words, delta capital phi, difference in total phase. And the reason we care about the difference is we don't really care, is it a crest, is it a trough, is it somewhere in between? We care about, are both waves doing the same thing, or are both waves doing opposite things? So the difference in total phase, which is basically just taking the stuff inside the sine function, the total phase, and applying a delta to each one, that tells you how offset the waves are. If the delta total phase is 0, that means the waves are precisely lined up, crest and crest, trough and trough, crest and crest, trough and trough. So that would be constructive interference. If the delta phase is non-zero, if the waves are offset by some amount, looking at exactly what that difference is gives you an idea of what type of interference you're looking at. So let's take a look at some examples or some possible values of that. If delta total phase equals 0, there's no difference at all. So you got crest and crest lining up, trough and trough lining up. So you get constructive interference. The waves are combining to make one large resulting wave. What would it have to be to get destructive interference though? If you want crest and trough lining up. Yeah, if delta total phase is exactly pi, it's destructive interference because 1 pi is how much of a cycle? Yeah, that's exactly half a cycle. So if we take a wave and then we take another wave that's exactly like it, well, close to it anyway, but then we take one of those waves and shift it exactly half a cycle. Half a cycle off means now we have crest and trough lining up, trough and crest lining up, crest and trough lining up. So that's destructive. They cancel each other out as much as they possibly can. Whereas if there's no difference, then they line up precisely. But what if we push that further? If delta total phase equals 2 pi. 2 pi means how much of a cycle? Yeah, one whole cycle. And if we shift this exactly one whole cycle, so we take one of the waves, let's say we leave one of the waves where it is, but the other one we shift exactly one whole cycle. Now what kind of interference is that? Right, it's constructive again. Or if we move it another half cycle, so we get 1.5 cycles, so that'd be, what would 1.5 cycles be in radians? Yeah, 3 pi, and that gives us destructive. Or if we keep going one more half cycle, because every half cycle we get a change, that would be 4 pi, because an extra pi is half a cycle. So if delta total phase is 4 pi, it's constructive again. So we get this repeating trend. Every half cycle, every extra 1 pi, we change what type of extreme interference we get. Constructive, destructive, constructive, destructive, constructive, and so on. And what's the pattern here? When do we get destructive versus when do we get constructive in terms of difference in total phase? What do you notice about all of these constructive values? Yeah, the even ones, even multiples of pi are constructive. Odd multiples of pi are destructive. Because 2 pi is a whole cycle. So any even multiple of pi is a whole number of cycles. Any odd multiple of pi is exactly something and a half cycles. So looking at these individually, we've got constructive interference occurs when offset is, that is delta total phase is a whole number of cycles. In other words, even times pi. Alternatively, how could you write any even number? What's our usual expression algebraically for an even number? It's just multiples of what? Yeah, 2n. So you could write the even number as 2n, or you could even write that as 2 pi times n, where n is just some whole number. And I think writing it as 2 pi times n emphasizes that it's a whole number times a full cycle, whole number of cycles. But it's sometimes more useful to think of that as an even number, 2n times pi. And that's going to result in a very large amplitude, large oscillations. In fact, the largest possible. And then the other extreme is the destructive interference, which occurs when delta total phase is something and a half cycles. And how would we write that in terms of pi's? That is in terms of radian measure. Yeah. Well, I would put the +1 in parentheses. We'd have, because if we want to get, ultimately we want to get an odd number times pi. So you could write that as 2n plus 1 times pi. Because 2n is an even number, 2n plus 1 is an odd number. So we want an odd number times pi. Alternatively, we could write that as 2 pi times n to get a whole number of cycles plus pi. That plus pi is the extra half cycle. The thing is, the first whole number of cycles doesn't really change anything. It's the extra half cycle that makes it destructive. And what would that result look like? Like if you've got two water waves in a pond and they interfere destructively, what would you see at that point in the water? Yeah, either nothing, either it's going to be just still and flat, or maybe small oscillations. If the two waves are the same amplitude and you get destructive, they'll cancel out completely. If they're different amplitudes, like let's say one of them is amplitude 5, the other one is amplitude 4, 5 and 4 don't completely cancel out. You just get an amplitude of 1 as the result. So this results in small oscillations, the smallest possible, or none at all.
Oh, I had a question. So for this interference, the amplitudes don't necessarily have to be the same for each wave, correct?
Right. You could get, for instance, let's say we're talking about water waves. Maybe you've got one wave that has traveled a long way, so it has dissipated and it's very weak waves. And the other wave is really close to the source, so it's still very strong waves. In that case, the amplitudes don't match up. So they can't possibly completely cancel out. They can just cancel out as much as possible. Or if you're talking about sound waves, maybe you have a really loud sound and a really quiet sound. Even at completely destructive, they can't cancel out because they're not the same amplitude, but they can cancel out as much as possible. So that means you won't get no sound, but you'll get as quiet a sound as possible. But if they have the same amplitude, then they can cancel out completely. Any other questions on that so far? So that's generally how you would interpret the difference in total phase. We don't really care what the total phase is. We just care about the difference in total phase between one wave and the other, because that's talking about how much offset there is. But notice that in the total phase equation, when we apply a delta to everything in the total phase formula, we could have differences in any of these terms. We might have a difference in the phase shift term, the phase constant, and that's related to these sources themselves. Like if the sources are pushing and pulling in sync with each other, there's no difference in phase shift. If they're out of sync with each other, there will be a difference in phase shift. So that can be possibly a term involved. There could be a difference in position and wavelength. So that might play a role. There can be a difference in frequency. There isn't really going to be a difference in time because the waves are all arriving at the observer's location at the same time. But there could be a difference in frequency if the sources are like playing different notes, for instance, if it's a sound wave. Any questions on that so far? So let's take a look at how we might set up an example. Maybe if we're talking about, say, 2 speakers, for example. That's a very common situation in cases like this. A little bit. Let's say we have a speaker here, and then we have another speaker over here. And let's just call these speakers A and B. And let's assume they're producing the same frequency. Let's say the frequency equals 500 Hertz for each one. They're both producing the same note. And let's say you as the listener are standing right here. If you're standing here listening to both of these, what terms in the total phase equation are going to be important? Is there anything we know is not going to be different when we compare the two waves? Versus, is there anything that we know is going to be different? What's probably the most important difference between a wave from A that you hear and a wave from B that you hear? Yeah, we know we've got the same time component. There's no difference in time because you're listening to both of them at the same time. Also, they're both the same frequency. So delta frequency is going to be 0. They're both producing the same note. In fact, generally this time term only matters if the frequencies are different. And in that case, it becomes the most important one. But in this case, we can ignore it because the frequencies are the same. Yeah, there's a non-zero difference between the path lengths. This delta x here is really talking about the distance traveled by the two waves. So we have a wave traveling from speaker A to the listener's location, and a wave traveling from speaker B to the listener's location. These would be called ray traces, and because you could draw out arrows in all directions. There's rays of sound. We usually talk about rays of light, but you could talk about rays of sound also. There's rays of sound spreading out in all directions from each one of these speakers. So we could, in principle, draw out rays from each of these speakers in all directions. But we don't really need all of those. All we really care about is the sound that gets to the listener's location. So we'd only bother drawing in the rays from each speaker to the listener, each source to the observer. And we could call those distances, let's say x sub A and x sub B, the two different distances traveled by the different waves. So those would be the path lengths. Since those are different, that's going to be the most important factor in the total phase equation here. So if we were to write this out, we get total phase equals all this stuff. Let me put this on the other side. We know there's no difference in frequency, so we can ignore that. What do we know about the wavelengths of these two sound waves? Yeah, they're going to be the same. And since it's the same, we can factor that out of the delta. So we'd have 2 pi times delta x divided by lambda, the constant wavelength. And there might also be a phase shift. The thing is, the phase shift here, phase shift is really all about the sources and whether the sources are synchronized with each other. Generally inside a speaker, you've got a membrane called the diaphragm that's being pushed forward and backward by a tiny electric motor behind it. If the two sources are pushing in sync with each other, if they're both pushing at the same time, both pulling at the same time, there's no difference in phase shift. If they're out of sync, like one pushes while the other pulls, creating a crest while the other creates a trough, what's the difference between a crest and a trough in terms of radian measure? Right, you'd be offset by exactly pi. So if these two sources, if they're pumping out waves exactly opposite to each other, crest versus trough, trough versus crest, delta little phi would be exactly 1 pi. And that you can typically arrange with speakers by just wiring them oppositely. Like if you look at the back of a speaker, there are 2 ports for cords to plug in, one positive terminal, one negative terminal. If you unplug the cords, swap them, and plug them back in the wrong order, then the diaphragm is going to push when it should be pulling and pull when it should be pushing. So if one of them is wired in the normal way and the other one is wired in the opposite way, then you'll get a delta phase of exactly 1 pi. If they're both wired the same as each other, you'll get delta phase of 0. But either way, if you know that value, you can take the distances and look at the difference in path length. Like let's say you know both of these distances. You can subtract the distances to find delta x and calculate 2 pi times difference in path length divided by the wavelength. And assuming there's no phase difference, that value tells you delta total phase. And then based on what that is, whole number of cycles or something and a half cycles, you can tell if that's constructive or destructive. Or if it's neither one, if it's not something that's a whole number of cycles or something and a half cycles, that would just be called partial interference. It's just somewhere in between. Any questions on that? Does it matter if you subtract b minus a or a minus b? It doesn't matter about the order as long as you're consistent about it. So what you want to do at the beginning of the problem, make a choice. Are you going to subtract a minus b or b minus a? And just make that choice and stick with it throughout the entire problem. So make sure you're being consistent. In fact, it's a good idea to just write off to the side in this problem, delta equals a minus b, or whatever choice you make. Just write it down as a reminder to yourself and anybody else who might be reading it later, so that you can make sure you're consistent about it throughout the entire problem. Any other questions on that? All right, then try making use of all this stuff on your next FNT. There's probably going to be a lot of practice problems on interference, and we can go over some more examples next time. Feel free to email me or contact me in the Discord if you want to have any other questions, and I will see you next time. You're welcome.